Uh, it is my pleasure to introduce our speaker, invited speaker this morning. Professor Hernandez Lerma is an emeritus professor of the Department of Mathematics at SimO. He's a leader in the different areas of applied mathematics in stochastic optimization. He has written more than 120 papers in different areas like dynamic games, stochastic systems, optimal control. Also, he's author of 5 or 6 books, and some of them are actually the basic reference in stochastic optimization. Also, he has supervised more than 20 PhD students in different areas. So thank you very much, Professor Hernandez Lerma, and he will talk about dynamic games. It is my pleasure to introduce our speaker, invited speaker this morning. Professor Hernandez Lerma is an emeritus professor of the Department of Mathematics at SimO. He's a leader in the different areas of applied mathematics in stochastic optimization. He has written more than 120 papers in different areas like dynamic games, stochastic systems, optimal control. Also, he's author of 5 or 6 books, and some of them are actually the basic reference in stochastic optimization. Also, he has supervised more than 20 PhD students in different areas. So thank you very much, Professor Hernandez Lerma, and he will talk about dynamic games.
Thank you very much for the presentation, Daniel, and the organizers for the invitation to give this talk. I want to make just a comment about what Daniel said. I said that I'm an emeritus professor, and which is true, but emeritus in Mexico doesn't have the same meaning as in other countries. As you know, in Europe, in the United States, almost everywhere, emeritus means retire. You know, whereas in Mexico, emeritus is like an honorary appointment. It means professor for life. So it has a different meaning. You know? So in other words, I'm not retired. I'm very active. I also want to make a comment about my talk, you know, because I was planning to talk about randomized strategies with some mention in some applications, in particular game theory. But when I was preparing the talk, I realized that it was a lot better to do it the other way around. In other words, to speak about games and then give you an idea where randomized strategies enters into this picture. Right? So the idea is to give you an introduction to dynamic games, some of their applications. The talk includes cooperative and non-cooperative games, and some special cases, for example, compromise solutions, zero-sum games. It also includes some recent results on the existence and characterization of dynamic potential games. This is a very interesting class of games, which has become very useful in several subjects because, as I'll show you, it's very easy to compute the what is called non-cooperative equilibria. In particular, from this definition of potential game, you can easily deduce conditions for Nash equilibria to be the same as Pareto equilibria, which in general is not the case. So these are two different concepts. So the plan of the talk is, is to say a few words about what is a game, some particular classes of games, some historical remarks and examples, and then the main topics, cooperative games and non-cooperative games, as well as some special cases. So what is a game? A game is a mathematical model of conflict or bargaining between decision makers, which can be individuals or governments or countries. And they are called, these decision makers are called players or agents or controllers, depending on the context. So there are several ways of classifying games. First classification is in namely like flipping a coin or something like that. Then you have repeated games, which are the same as a repeated game is a static game that you keep repeating several times or even infinitely many times. And then you have dynamic games, which is the topic of this subject, this talk, in which the state of the game involves a dynamical system, right? So this is precisely the kind of games that I want to talk about. And a remark is that a one-player dynamic game is called a control problem. This is just a remark, but it's very important because there are many game problems that are reduced to one-player games. So now where you have a game and mathematically some games can be reduced to study one-player games. Now about some historical remarks. The study of strategic games can be traced back to the 18th century at least. For example, the earliest minimax solution of a game was proposed by James Waldegrave, an English nobleman, in about 300 years ago, in 1713. By the way, this minimax solution is one example of a randomized strategy that I will define in a few minutes. However, the strategic games receive widespread attention with the publication of this famous book, Theory of Games and Economic Behavior by von Neumann and Oscar Morgenstern in 1945. This was like the detonator of game theory. So this book concerned two-person zero-sum static games exclusively, but it spawned many fundamental ideas, and in particular dynamic games. So for example, as early as 1945, Abraham Wald introduced what is called the minimax approach to statistical decision theory. Another important contribution was John Nash's thesis in 1950. He introduced cooperative and non-cooperative games, bargaining games, many concepts that became fundamental for the development of game theory. His work had so much impact in economics that he received the Nobel Prize in Economics in 1994. During the Second World War, there were a lot of activity in games, by the military, but all this work was classified. It became, after the war. So in particular, they study anti-submarine warfare, persecution, event strategies. And the name is very natural, persecution evasion games, because when an airplane detects a submarine, the radar signals used by the by the airplane to detect the submarine are also detected by the submarine itself. In other words, the submarine knows when it's being chased, or persecuted by the airplane. And as soon as the submarine knows that it's being persecuted, it begins some evasive actions. So that this is why it's called persecution evasion games. Another important contribution was the introduction of differential games. In differential games, you have this is the state of the system, a time t, x, which is a function of the time t, the state x, and then this vector a sub t, which is the vector whose components are the actions of the different players. We're assuming that we have a capital N players in the game. This became very popular, in particular by the work of Isaacs, who wrote many books on these kind of games. By the way, Isaacs was also doing persecution evasion games for missiles versus enemy aircraft. The ideas were similar, but not quite the same. Another important contribution was by Shapley in his 1953 dissertation. He introduced what we now call discrete time Markov games. An example would be in the discrete time case when you have this state of the game at time t plus 1, which is a function of the state of time t, some random variables, some perturbations. And then you have again this vector a of t, which is the vector with the components being the player's actions. In 1960, Fleming introduced stochastic differential games, where you have a stochastic differential equation, the typical equation, except that the coefficients, the drift and the diffusion coefficients depend on, again, the actions of each player. And then there are many other classes of games, like jump games, hybrid games. This game theory has had a lot of impact in economics. Many people from game theory has received the Nobel Prize in economics. For example, Shapley last year, Thomas Sargent, Eric Maskin, Myerson, and so on. So I mean, this gives you an idea that game theory has had a lot of impact in economics. But that is also the case in many other areas. For example, in operations research, a few weeks ago, I checked in MathSciNet, and there are over 1,900 matches, for operations research and games. There are also environmental games, including exploitation telecommunications games, in portfolio games, in advertising, money laundering, e-commerce, epidemics, and so on. This is one of the characteristics of game theory, which is applicable to many interesting situations. Just aware about the strategies. In a few words, a strategy is a rule for making decisions. So in the simplest case, you can imagine a decision problem with state space X, an action set A, and a deterministic strategy is just a function from X to A that tells you that if the state is X, you choose this action, f of X. Right? I'm going to call capital F the set of deterministic strategies. And a randomized strategy is actually a collection of probability measures. So it now depends on two variables, right? And what you have is that if you fix the state X, then you have a probability measure on A, on the action set. And if you fix the set B, this is a measurable function on the state X, right? So it's just a family of probability measures. And when you write phi of B given X, it means that you're taking an action with probability, with this probability, you take an action in the set B, given that the state is X. And something very interesting, is because it's very important for applications and for mathematical purposes, is that the set of randomized strategies is a convex set. And under some natural conditions, you can compactify the space and so on. So it's very nice from a mathematical point of view. And it turns out that the set of deterministic strategies is the set of extreme points of the convex set. That's another very useful mathematical property. Speaking of examples, there's a very common example called the US-Canada fish wars, which is about the salmon fish. Salmon spawn and dies in this part of the United States, in the states of Oregon and Washington State, and also in British Columbia on the Canadian side. And what happens is that between spawning and dying, the fish migrate to the sea, and then all along the coast, the United States, Canada, Alaska, the Northern Pacific, and then come back to land, to die to reproduce and die. Right? So the question is, whose fish are they? Americans this side claim that the fish is theirs. Canadians say the same, and so on. That creates a lot of political problems. For example, some years ago, a group of Canadian fishers stopped a Alaskan ferry in a place near Vancouver. They stopped the ferry for about 3 days. Which caused a lot of problems. And in retaliation, the Alaskan government stopped the ferry stops in this area of Vancouver. Which again, this was created a lot of millions of dollars in losses, for this retaliation. So, this is an interesting example because you can see almost any kind of situation that you would study using game theory. For example, if you look at a single fishery, at any point, just at a single fishery, you would expect that fishers cooperate between them, right? There's some kind of cooperation. Whereas if you look at different fisheries, for example, in Canada and the United States, you would expect that they are rivals. You have a non-cooperative situation, where each fisher is trying to grab as much possible fish, right? And another class of games, you have, for example, state governments or governments, controlling fisheries, for example, to control the harvest by different fisheries. Yeah? So in other words, you have a lot of kinds of situations that you would start using game theory. So in the simplest case, if you look at a single fishery, for example, you will have the state of the system in discrete time. This would be the population size, that t plus 1, which is a function of the state at time t. You have to subtract the harvest, by the n, capital N players. And then in addition, you have some kind of random perturbations. This g of x is what is called the population's natural growth function, which has different forms, depending on the species. In the continuous time case, you would write this as a stochastic differential equation, where you have the drift term very similar to this case, right? And then you have a random term. So in this problem, each particular player wishes to optimize a given objective function. So, for example, the player I would try to, for example, if you see this like a cost function, okay, each player would try to minimize this, which is this expected value of this sum of discounted cost. So you have this alpha I is a discount factor. The cost function at each time t depends on the actions of all players, right? So this pi is actually is the set of the collection of all these actions, A1 up to A capital N. Okay? This is defined for every initial state and each multi-strategy pi. In other words, each pi is the strategy for player I. Another very interesting and common example is oligopolies. An oligopoly is a market with few sellers or firms or producers and a large number of buyers or consumers and so on, right? The word oligopoly comes from the Greek oligos, which means few, and an abbreviation of monopoly. So an oligopoly is like a monopoly by a few group, a small group of producers or sellers, right? Which control a very big market. For example, all kinds of transportation services like airlines, trains, buses. You have a certain number of small airlines, controlling the whole market. Or in energy markets, you have a few companies controlling oil, gas, electricity, whatever. Right? So a typical example would be when you have N producers, and this would be for example, the stock level of player I at time t+1, which is a function of the stock level time t, then the amount that player I produces minus some, for example, the demand or some other kinds of perturbations. In this example, typically what players can control is the production size and the price, right? So this A sub t, these actions are vectors like this. A very well-known example is the Cournot duopoly, which is very interesting because this was the first example of game theory in economics. Cournot was trying to control the production size, whereas Edgeworth a little later introduced the price game, controlling the price. And the work, Cournot's work, was so thorough, so complete, that an author wrote that the oligopoly theory began with Cournot more than 140 years ago. Judging from many intermediate textbooks on price theory, one might think that it ended with him too, because of this fact, that Cournot's work was very, very thorough. And he anticipated many of the concepts we deal with nowadays. So going back to games, as I said at the beginning, there are two large classes of games, cooperative and non-cooperative. In the cooperative case, you have players act as a group and coordinate their actions for their mutual benefit, whereas in the non-cooperative case, players are rivals and each of them acts in his own best interest, paying no attention whatsoever to the fortunes of the other players. So it's, we have this large classification of games, and I'm going to give more mathematical details, I'm going to use this notation, which is very common. If you have two vectors in Rn, with capital N is the number of players, we write u less than or equal to b if and only if u sub I is less than v sub I for every component I. So if this is the vector v, then the set of vectors that satisfy this condition are all the vectors u in this quadrant. And we write u less than b if we have, again, this condition, but u is not equal to b. So we have again, the same set, the same quadrant, without this point, without the point v. And more notation, we're going to fix an initial state, which might be random, right? And we call v sub I, this is the cost function for player I, which is a function of the initial state and also each multi-strategy pi, which is a function of, in other words, this vector, this is called a multi-strategy. It's a vector in this product set. And we call v sub pi, v of pi, the set of these cost functions for all players. So this is a vector in Rn, right? And if you switch, so if you vary this pi, then you get a set in Rn, which is called the game's objective set. And then using this set, we can define a Pareto equilibrium or cooperative equilibrium as follows. We have a multi-strategy pi star, which is called a Pareto equilibrium. If there is no pi, there is no multi-strategy pi that gives you a cost vector less than v of pi star. So for example, if you have a point here, this obviously doesn't give, it's not in a Pareto equilibrium, right? Because if you take if you have a strategy that gives you a cost vector here, there are many cost vectors below this one, right? Below this point. So actually, the set of Pareto equilibrium is going to be the multi-strategies that give you cost vectors along this part of the boundary, which is called the Pareto front. Right? And a very nice result. You know, actually, some mathematicians say that cooperative games are not interesting because they can be reduced to a single optimization problem. In the following sense, under some hypothesis, a multi-strategy pi star is a Pareto equilibrium if and only if there is a vector lambda with positive components such that pi star minimizes this scalar function. You know, this is scalar product of lambda times v of pi. Okay? So in other words, we have n players. However, in the cooperative case, the problem of finding a Pareto equilibrium reduces to solve a scalar problem. You want to minimize this scalar function. So the question is, why is it called a cooperative equilibrium? I mean, in what sense is cooperative, right? So it is a cooperative performance of it, the performance of the others. For example, you know, you can see this here. You know, if you move, this is V1, this is the cost for player 1, this is the cost for player 2. If you move to the left, you know, along the Pareto set, you know, along this line, if you move to the left, V1 is decreasing. In other words, player 1 is improving his situation, right? Because his cost is decreasing. But the cost for player 2 is increasing. Okay? And similarly, if you move to the right, then V2 is decreasing, but V1 is increasing. So this is what it means, you know, that no other joint decision of the players can improve the performance of at least one of them without degrading the performance of the others. So that leads to a very interesting decision, a question, because you know, one player is improving his situation and the other guy is going worse. You know, so the obvious question is, when is a cooperative equilibrium fair to all the players? In other words, when all players are the happiest, let us say, you know. And, you know, it turns out that this question is very tricky. There is no single answer because it depends on your definition of fairness, right? What does fair means? Fair for what? Fair for whom, right? So a possible answer, very commonly used, is this one. For each player I, you compute the minimum value. In other words, you minimize the cost v sub I over all possible multi-strategies, and then you consider what's called the game's utopic or virtual or ideal minimum, which is the vector with these minimum components, right? In other words, this is the objective set. You minimize V1, it gives you V1 star, then you minimize V2, and this vector is the set of is what is called this utopic minimum, right? Which is called utopic because this minimum is not in the objective set. In other words, in general, you cannot expect to obtain this point, right? So that's the reason for calling this utopic or virtual or ideal minimum. And then a multi-strategy pi star is called a compromise solution with respect to some norm if v pi star minimizes the distance to this vector v star. In other words, you minimize this set, and if pi star reaches the minimum, then you call it the compromise solution. And this is very, as I said, it's a very commonly used definition of fairness because it has a nice interpretation. Huh? The difference v sub I of pi minus this minimum is called player I regret when you use pi star, and the difference then is called the group regret. So it's a very sort of a nice interpretation of pi star. And, but of course the problem is what kind of norm should we use, right? For example, if we have an infinity of LP norms, so which one is you should use, right? So for example, with P equal 2, you have the typical, Euclidean norm, right? And then pi star is called Salut-Wass's solution to the cooperative game. And if you get P equal infinity, you have this norm, and the pi star is called the minimax equilibrium, right? Because it minimizes this, the maximum of these differences. There's something very, very important, which is we're talking about dynamic games, right? So dynamic means that they are moving in time, they are evolving. So something that is an equilibrium today might not be an equilibrium tomorrow, right? Things are changing. So a very important thing is this one. A solution of equilibrium with a dynamic game is said to be time consistent or dynamically stable if its optimality is preserved throughout the game. In other words, you have time consistency if an equilibrium is it gives in an equilibrium during the whole duration of the game. Right? And there are many ways of. We're going to assume that our solution constants are dynamically stable, but in fact that there are many mathematical ways of doing this. A typical tool would be using dynamic programming. For example, this Jung and Petrosian have a whole book, on cooperative stochastic differential game, and the whole book's about how to define consistency for equilibrium, right? Or time stability. And this work by the same author, but it's for discrete time games. For non-cooperative games, we're going to have the same time consistency problem, right? And again, it can be done using dynamic programming or other tools, like this paper by a recent paper by two authors. Just to complete this, as another remark, there is the latest issue of the International Game Theory Review is a special issue on open problems in the theory of cooperative games. So in case, if you are interested in this topic, this is a nice issue, because it's give you like, as a mathematician, we survive at solving problems, right? So it's good to know that there are many open problems for cooperative games. Now, in the non-cooperative case, again, we have each player, now players are rivals, that they're pursuing their own interest. And in a Nash or non-cooperative equilibrium, one player cannot improve her outcome by altering his or her decision unilaterally. And what that means is the following. I want to explain first for the case of n equal 2 players. A multi-strategy pi star, which now has two components, right? It's a Nash equilibrium, also known as a non-cooperative equilibrium. Player chooses the minimizes his cost B1 in pi 1 star. This is what is called the best reply condition for player 1. In other words, player 2 fixes his strategy pi 2 star, and player 1, his best reply, is pi 1 star because it minimizes this the cost function V1. And similarly, if player 1 fixes his strategy pi 1 star, then player 2 minimizes his cost function. It is in pi 2 star. So this is the best reply condition for player 1. This is the best reply condition for player 2. And in the general case, this is the same definition, right? So if a multi-strategy, if you have a capital N players, a multi-strategy pi star is a Nash equilibrium. If for every player I, the player I minimizes his cost function in pi I star when all the other players fix their strategies. So this is the best reply condition for each player I. And something interesting, one of the reasons that finding Nash equilibrium is complicated is because you have to solve capital N control problems. Yeah? In other words, you have to minimize capital N functions, right? So that's the, and perhaps for this reason, it turns out that the existence of Nash equilibria for general dynamic games with uncountable state space is an open problem. In other words, if you have games with a finite state space or a countable state space, like in queuing games and so on, then it's very easy to show the existence of Nash equilibria. But if you go to the uncountable case, for example, R or Rn, then there are no general conditions, right? So there's a lot of work on Nash equilibria, but for special cases, for example, when you have games with some kind of a structure, linear games, convex games, and so on, some particular classes. And it turns out that due to this difficulty, there are many examples of incorrect results in the literature. Papers that are accepted, and a few years later, people realize that they were wrong. So, for example, this is a paper by Lai and Tanaka this is for a discrete time game, whereas this one is for a continuous time. Actually, in a stochastic differential game. The main results are incorrect in both cases. And these authors realized that the paper was wrong, so they, in 1996, they published a correction. And the problem is that some of these results are reproduced some years later. For example, the incorrect result in reference 2 was reproduced in this survey paper, on a stochastic differential games and application. So, in other words, these authors, they knew the 1992 paper, but they didn't know the correction in 1996. So you have to be careful with the literature. If you have a general result for dynamic games, probably it's incorrect. So you better be careful. So, as I said, one of the ways of solving non-cooperative games is studying special cases. A very common case is when you use what is called zero-sum games, which are so named because it means that the sum of the cost function of player 1 plus the cost function of player 2, the sum equals 0. So this means that this is the reason for this name, zero-sum games. So it means that V1 is the negative of V2. So if you call V this common value, it turns out that the Nash equilibrium is the same as having a saddle point. For example, if player 2 fixes his strategy, then player 1 minimizes his cost in pi 1 star. And similarly, if player 1 fixes his strategy, then player 2 maximizes his cost in pi 2 star. So you have this best reply condition, in this inequality. An interesting application. How much time do we have? There's a very nice application in something, this is very interesting because Abraham Wald, whose name I already mentioned at the beginning, he was studying optimization problems with unknown parameters. So in other words, you want to optimize a function, but you don't know the function itself. It depends on something you don't know, And he had this idea of studying these problems as a two-person game, in which strategy, the nature is trying to, or someone, is choosing the values of the unknown parameter, and the optimizer or decision maker is trying to optimize this other function, right? So in a typical case, you have, for example, a stochastic differential equation with unknown parameters, right? Or you have a discrete time problem, with the disturbances have a known distribution. So you don't know the distribution of these variables, right? So to fix ideas, we're going to consider the latter case where the disturbances are IID with unknown distribution. So how do you solve a problem if you don't know the perturbation distribution, right? So there are two general cases. It depends on this if these perturbations are observable. For example, in a queuing system, if you don't know the arrival distribution, you cannot solve the problem, right? But what you do know is that you can distribution, right? But or similarly, for example, in production systems where the perturbations is demand in each period, right? So you can use the demand in previous periods to estimate the unknown distribution. But if these perturbations are not measurable or observable, right, then an approach is to use minimax control. Just to give you an example of this is what is called a continuous casting process. It's to produce steel. It's the most common process to produce steel, right? So you have the molten steel coming from some source. This steel goes to some deposit called ndez, and from here it comes to the molds, and there are several important factors for the quality of the final product. And one of these factors is to control the steel comes here by what it's called gravity, right? So it's very important for several reasons to keep this level constant. Right? So one might say that that's a trivial problem, right? I mean, you want to control this level constant, it's trivial. But it is not, technologically speaking, turns out to be very difficult, because first of all, you cannot see the level of the steel here, because of the temperature is about 1600 degrees Celsius, yeah? And that produces some kind of dust that covers the molten steel. So actually you don't see the level, right? What other problems are there? There is a lot of, this turbulence and these kind of things, So there is no way that you can model this in a mathematical sense, right? So this would be a typical situation where you want to use minimax control. So in the minimax case, this, which is called a worst case control or robust control, were introduced by Abraham Wall in optimization in 1939. And what is interesting, is that the control problem is posed as a two-player game, where player one is the optimizer, the decision maker or controller, and player two is the nature that each time t chooses the distribution, say mu t of the corresponding random variable, psi t, where this capital M is the family of feasible distributions. Okay? Since you don't have too much information about these distributions, you have to take very general conditions. For example, distributions with a finite mean, or distributions with zero mean and second order, finite second order, second moment, right? So some very general properties. And then, now instead of having the controller's objective function, now you have a cost depending on two strategies. Pi is the controller's strategy, and gamma is the what is called the nature's strategy, that is choosing these unknown distributions. So now you have a function of two variables. You take the supremum of the nature's strategies, and you call pi star a minimax strategy if pi star minimizes this maximum. So you have the minimum of a maximum, so that's the name for calling this pi star a minimax strategy. And it is called a worst case control problem because a typical interpretation of this supremum is like the worst that nature can do. Right? So you are trying to control the worst case. Now, just to, I'm going to say a few words about potential games, which has become a very popular topic in game theory, and I'm going to explain why. In the static case, you have a game in what is called normal form, which has three components. Capital N, this calligraphic N, is the set of players. A sub I for each I is the set of actions, is the action set for player I. And then you have for each player I, V sub I is the payoff function for player I, which depends on is defined on this product set. You know? So in other words, this function Vi depends on the actions of all players. And in this case, the definition of Nash equilibrium is the same as before, right? We say that a vector A star in A is a Nash equilibrium for the game G if for each player I minimizes his cost function in A sub I star, right? So this is the best reply condition for player I. Right? The same one as before, right? So we say that a differentiable function P from A to R is called a potential for the game G if it satisfies the typical definition of potential function, in the sense that the partial derivative of V sub I with respect to AI is the same as the derivative of the potential function with respect to AI for every I. Right? So this is the typical definition in physics, right, of potential function. P is the potential function of a set of functions V1 up to Vn if P satisfies this condition. And in this case, if there is a potential function, G is called a potential game. Some important remarks is that if you look at these definitions, are more or less recent, right? However, potential games go to the beginnings of the 1950s and so on. And another important remark is that doesn't need differentiability. You know, I did it this way. The way it is defined a potential function in physics, right? It's a natural way of doing it. But in fact, you don't need this. You can define potential functions in a weaker sense. Right? That doesn't require differentiability. Now, this is the key result. Suppose you have suppose that G is a potential game with a potential function P. So you have a function that gives you if the derivative of the cost function but for player I, if you have this condition, then obviously V sub I increases in AI when P increases, and V sub I decreases when P decreases, and so on. So if you want to maximize V sub I, then you have to maximize P in the variable A sub I. And you do this for all players, right? So in other words, a vector A star is a Nash equilibrium for the game G if you have a minimum for all players. In other words, if you want to find an equilibrium in this case, instead of solving capital N problems, you have the minimization of a single problem, which is this potential function, right? This is in the static game, and in the dynamic case, a non-cooperative dynamic game is said to be a dynamic potential game if it can be reduced to a single optimal control problem. In other words, instead of having n optimization problems, you have a single problem. Instead of going to, I'm going to give you an example, just to see how it works. It's actually very, very straightforward when you're dealing with potential games. There is a class of environmental games called lake games, because in lakes, typically you have several communities using this lake in some sense, to get water for recreational purposes and so on, But the problem is that the communities also pollute the game, right? So that's in this particular stochastic lake game, you want to maximize this discounted equation. The state echo sub x is the the level of phosphorus in the lake. This function G sub I is the utility for discharging this kind of phosphorus, A sub T, and this is this utility for polluting the game with this phosphorus, right? So this is the problem, right? For each I, you want to maximize this function subject to this state equation, where this Vi is the sum of these actions for all j not equal to I. Right? Now we define this potential function, which depends on the actions and the state x, as the sum of these utilities Gi minus x squared. Right? And then you can easily see that this is potential function because if you compute the derivative of p with respect to a sub a, the ai, the derivative is the partial derivative of gi with respect to ai, which is the same as the derivative of this function, right, with respect to ai. In other words, when you compute the derivatives of this function, you get the derivatives of these utility functions here. Right? So this is why you have a potential for the lake. And then you can easily see that if you have a solution for this control problem, where you now have the potential function, instead of the player cost function for players, and you have a potential function. If you solve this control problem, the solution gives you a Nash equilibrium for the stochastic lake game. And this is very easy to see. You know, it's just a one-line calculation, you know, but I will not do it. But you can verify, you know, for player 1, player 2, and so on, for each player, you have this best response condition, right? I mean, best replied condition. So in other words, you check the best replied condition for player 1 and then for player 2 and so on, you know, and that gives you this property of potential games. You know? And now to conclude, you know, as I showed you at the beginning, you know, the cooperative equilibria and non-cooperative equilibria are quite different, you know. But if you look at the definition of a potential function, right, you remember to define cooperative or Pareto equilibrium, you do it by solving a convex combination of the cost functions of the different players, right? Now, if you interpret this as a potential function, in other words, if you can show that one of these convex combination is actually a potential function, then finding Pareto equilibria is the same as finding Nash equilibria, right? And this is precisely the case, which I'm not going to do, but there's a nice example, again, about what is called the Great Fish War, which is a very well-known example by Lefkari and Mirman. It's very well-known, but because they introduced this fishing game, and they could compute explicitly Nash equilibria, Pareto equilibria. They compare them and so on. So it became a fundamental paper, you know, when dealing with stochastic, population games. And it's we have to conclude. It's you know, if the convex combination of the corresponding, you have this is the function for player I, and this is the convex combination of the different objective functions, you know, for players. With these lambdas are positive numbers that sum up to 1, and it's very easy to see that the non-stationary Markov strategy, it is called Markov because it only depends on the current time t and the current state x hat, and it's very easy to see that this Pareto equilibrium also gives you a Nash equilibrium. And the way you do that is exactly as I did it before, you know, just a straightforward calculation. And I think that's it. Thank you very much. If you have any questions, yes. Yeah. Yeah, as I said, there is a very large class of games called environmental games that includes pollution, warming, a lot of cases. Yes, there are, yeah. Actually, if you go to Matsainet, one of those, and you write environmental games, you're going to get a big list of publications. Yeah.
Okay. Any other question? Yes.
Oops, it's 35.
Thank you.
Oh. I cannot go backwards, I think.
That's fine. On that page, you mentioned that the case of an uncountable dimensions is an open problem.
Yes.
Does that mean then the case of a countable, there it is, countable but infinite dimension is not open?
Yeah, the problem is, when you have a countable space, everything is very nice, but because in countable sets with the discrete topology, all functions are measurable, actually continuous, compact sets are finite, and so on. But when you go to the uncountable case, right, then you have to be, there are rather measurability and topological problems,
Yes.
and it turns out there's no general result.
Yes, so countable infinite is a solved problem already.
Yeah.
Yes, thank you.
Any other question? Well, okay. For the idea of introducing the randomized strategies for control problems is to transform somehow the problem into a convex problem, right? And then solve it. So this idea can be translated also to dynamic games, or?
Actually, that's one reason for doing it. And many people, in the 20th century thought that the main reason for introducing a randomized strategy was a mathematical reason, to convexify the problem and these kind of things, But it turns out, as I saw you in this persecution evasion games, there are cases in which you have to use randomized strategy because you don't know what your opponent will do, So you cannot say, if this guy does this, I do this. No? But you don't know what your opponent will do. No? So there are many cases, very elementary examples where Nash equilibria do not exist. In the deterministic strategies, you have to go to the randomized case.
Okay, if there are no more questions or comments, let's thank again Professor Lerma for his talk.
Thank you. Thank you, Isabel.
Eso es de lo era.